So I'm going to give a talk that's more like a start to end project where I was trying to deploy modulation recognition on an RFSoC that was running a deep learning model. So to begin, I'm Andrew. I'm a research assistant at StrathSDR, which is a research group within the University of Strathclyde. I'm currently writing up my PhD, which is focusing on deep learning inference for physical layer wireless comms on software-defined radios with system on chips. Previously, I've done a few internships over the PhD, at AMD and at MathWorks, working on two different things. So I was in the Pink development team for the bring up of the second RFSoC board that was released by Xilinx at the time. And at MathWorks, I was working on HDL for wireless blocks for 3 summers. My most recent degree, I guess, is an MEng. It's an MEng degree, and that was achieved in 2018 from Strathclyde. So this talk will present an FPGA-based CNN architecture that is designed for continuous and uninterrupted radio data processing with a specific focus on this application of modulation classification. So we'll cover the motivation for deploying deep learning for physical layer applications. Then we'll cover a CNN data flow architecture design that I custom made from like basic principles, just so I could get the hang of it and understand it better. And then go through a little bit of the design choices with that. Then the dataset generation process, where I've made my own dataset to train the neural network, and I've created that with deploying it on the RFSoC in mind. And then we're going to talk about training of the neural network with specifically quantized aware training. And then we'll go over a little bit of the performance of the network at various quantizations and signal to noise ratios. And then I'll talk a little bit about the Pink framework and how we look at interactive plots using Pink. So the motivation for deep learning for wireless comms, well, deep learning has emerged in various fields, as we're all aware, from things like computer vision for object recognition, natural language processing for like language translation, and these huge data centers of networks that are being used by things like OpenAI. And then we have the field of wireless communications, where it can benefit from deep learning for things like channel estimation, signal identification, decoding, and so on. And as 5G and 6G technologies emerge and are implemented, deep learning could play a more crucial role in all layers of this communication stack. And so my focus was a little bit on seeing what radio transceivers are being used and how they're being used right now for radio transceiver pipelines, and seeing how we can swap in and swap out a deep learning model reusing these transceivers. So in terms of like a little bit of context, because when we use deep learning, it can mean a big range of things, the different neural network sizes. So how large are we talking here, right? So if we look at GPT 3.5, which is the previous version of ChatGPT's OpenAI model, that's from what estimates say is 175 billion parameters, which is implemented on tens of thousands of graphics cards. Then we have things for like object recognition, something that you could run maybe on a singular graphics card. It kind of has like maybe 9 to 15 like layers in total, and maybe you could squeeze it onto a system on chip device. And then in our case, what we're talking about here is a radio ML model, which runs on maybe 4 layers and only has 260,000 parameters. So this is kind of gives you a little bit of context as to what kind of size networks we're working with here. And that would allow us to deploy on smaller edge devices. So the motivation for deep learning would, so if we look here, we have a typical radio receiver system. So we have an ADC, it's tuned to a specific center frequency, decimated, and maybe we have something like some synchronization, demodulation, channel estimation, and decoding. And what we're looking at here is just swapping out this functionality and keeping this this streaming of samples and this radio pipeline in place, where we have maybe storing the weights on chip just to keep that model flowing. So I'm going to introduce the AMD RFSoC, which stands for Radio Frequency System on Chip. It's the next family after the MPSoCs from AMD, which are system on chip devices that combine high accuracy ADCs and DACs and can operate at many gigasamples per second and include programmable logic, so you can implement your own custom algorithms. The results that I've done for this, the stuff I'm talking about in this presentation, I've done with the RFSoC 2x2, which is a Gen 1 device, but I'm kind of hoping to move on to a Gen 3 device and a more recent device, such as the RFSoC 4x2. So we're interfacing with these boards using a framework called Pink, and that utilizes like the Python language and libraries to communicate with the bit stream on the development board. And we'll see more about that later. So this work builds, so the prior work that this work builds on top of. At first, I want to talk about deep learning for wireless communications. So things like the first paper that did modulation classification for deep learning neural networks. So that was done by O'Shea et al. And they provided a neural network architecture and a data set that became like a benchmark for the rest of the industry to test their networks out on. Then in terms of deploying deep learning models in a data flow like structure, we have Umuroglu et al. From AMD, who their team released Fin, which is a framework for binarized neural network inference, and that was done in 2017. And then there's been a couple works since then, and maybe more that I might have not found, but where they combine these two fields, so with the RFSoC. So another AMD sponsored project where Radio ML meets Fin. That was a concept paper that was released by the Fin team. And then another group, Trigdal et al., who implemented a real-time AMC classifier using the RFSoC. And I think their demo was demonstrating maybe 3 modulation schemes, but maybe they've implemented more since I last checked. So the application in mind that we have is modulation classification, and that is a task of identifying which modulation schemes are being used in a radio signal. So the modulation scheme refers to the process of encoding the information onto a carrier signal for transmission, and these are done in different schemes. And this, as I said before, builds on the prior work from O'Shea et al. And we're using 8 modulation schemes in this work. So DeepSig, which is O'Shea et al.'s later company, their radio ML dataset quickly became a benchmark for testing deep learning architectures. But the radio ML dataset does not really represent what we receive to the ADC on an RFSoC, and it doesn't factor in degrading effects that may be induced by the transceiver itself. So things like stuff that happens during the up and down conversion stages, any data converter spurs and harmonics, ADC quantization, maybe some interleaving stitching. So, and radio ML is provided in short frames. So real-time classification would require maybe a continuous stream to be received. So we kind of went through the choice of maybe we should generate our own data set using the RFSoC as part of the generation loop. So to begin with, we're using MATLAB and specifically the communications toolbox. And we begin with some random data in a frame. And then we'll modulate that to one of the 8 modulation schemes. We'll then pulse shape that, pass it through a Rissian channel, clock offset it, frequency offset it, maybe do some time drift, and then add noise ranging from -20 dBs to 24 dBs. And then we'll package that as our transmission data, which will be 4,096 long complex samples per frame. And each modulation scheme will have around 1,000 frames. So we'll take these 4,096 long frames into the processor and store it on the processor DDR. We'll then read from the processor DDR via direct memory access IP and pass that to a cyclic buffer, which will constantly read from these 4,000 samples and send that to digital conversion stage and then pass it through a DAC, which will be then received in loopback, received in the ADC, and then down converted and then captured in 128 long complex frames, and then will be passed back to the DDR. And this is how we're going to build our data set for training on neural network. So once we've made our data set, we want to take the set and then split it. So sorry, the set itself is around 2.6 million frames in total, with like 300,000-ish frames per modulation scheme for all the varying SNRs. And then we'll split that data set into 80% for training, 10% for validation, 10% for testing, as is good practice. And to train this, we'll use a framework called Brevitas, which is a fork from PyTorch, where they have converted maybe some convolutional layers to include quantized weights and activations. So this allows us to do quantized aware training. And yeah, the quantized aware training allows for the network to be aware of the dynamic range of its weights within the training loop. So it becomes part of the loss function or part of the noise that is part of the network. And this results in better performance and quantizing after training. So the network dimensions you can see on the right here, it's not very big, but it does the job. So we have two convolutional layers and two fully connected layers with ReLU activations and a softmax at the end. And then we have three different networks that we're gonna train. We're gonna train one with 16-bit weights, 16-bit activations, 8-bit weights, 16-bit activations, and 4-bit weights, 16-bit activations. So once we've trained our networks and we're happy with our training process, we then want to implement this onto a CNN architecture that's running on the RFSoC itself. And so I went with the perspective of maybe I should build this from basic principles just to see what happens, see what I can get done. And I had a specific goal in mind where I wanted the model that processes every sample that is received into the model without pausing or slowing down the input. So it has to process every single sample that it receives. And a streaming model like this means that the latency for it to give you an answer is deterministic, given your clock rate, your network dimensions, and whatever resource sharing factors you may have. And a deterministic latency means that the deep learning model can be synchronized with other aspects of the receiver design. So it means you can assist with slotting it into this receiver pipeline. So the design philosophy is a data flow-like model, which keeps samples constantly streaming in and out. And one of the significant challenges of this when applying this to deep learning, and specifically with convolutional layers, is that convolutional layers can have an increased production of samples compared to what you input. So you might input a certain number of samples into the convolutional layer and you'll get more than you put in on the output. So the overall clock rate has to increase to address this challenge. And the design tools I used were simply HDL Coder and AMD Vivado, so I could implement this onto the board itself. So in terms of our input data processing, we'll receive an IQ signal that's digitized to 16 bits, because that's what the ADC will give you. And then we'll low pass decimate this by a factor of 32, and then we'll interleave it so that we have a real sample and an imaginary sample coming in one after the other. And then we'll collect those together and then burst the data. So they come in they leave this subsystem that we see here as frames. And so the sample rate that we receive from the ADC will be 128 megasamples per second. And once we've decimated, it'll be around 4 megasamples per second. So firstly, our convolutional layers, we're going to implement a transform that simplifies the convolutional layer calculation into a matrix multiply. That's the generalized matrix to matrix transform. And it's simpler to implement in hardware because it means we can more easily do things like time sharing resources rather than having to keep track of where the kernel is over the input frame. The way we implement this in hardware is we buffer the samples coming in to each convolutional layer, and then we use like a state machine or what I call here a sliding window controller to read the samples out of the buffer in a certain order to perform this generalized matrix to matrix transform. And then these are multiplied with the rest of the weights that are stored on chip. So, and then the rest of the layers are more simple to implement. So fully connected layers are just a simple matrix multiply. There's no transformation needed, and we can do the same thing here where we hardware resource some of the multiply accumulates depending on what we want, a shorter latency or higher resource cost, or vice versa. And it's important to note that fully connected layers do not influence the requirement for increasing the clock rate. So we really only need to consider this for the convolutional layers. And then we have a bias that is saved to 16 bits, and that's just simply added. And to implement our Rayleigh activation, we'll just implement a simple max function. So anything below 0 is set to 0. So the overall architecture looks like this. So we have our processing system on the left. We use Jupyter notebooks to load our 4,000 sample frame onto a DDR. Then that is read by DMA, past our cyclic buffer, and then constantly being sent to the DAC through an interpolation chain. Received an RF loopback to the ADC, decimated, and then passed through the neural network where the answer is sent back to the processing system in Jupyter. And at the bottom, I've tried to unroll what I've implemented in hardware for the convolutional layer. And yes, the 4 layers can be seen clearly here, where we have the sliding window controller for each convolutional layer, where it reads the samples into the buffer, and each of the matrix to vector multiplication stages here, where we might have some different resource sharing factors in those boxes. So I mentioned earlier that we use Jupyter notebooks to read to send the data that we want to test and then read it back. And how are we doing this? So we're doing this through Pink. So Pink is an open source project from AMD that makes interfacing with system on chips a lot easier. So it uses the Python language and libraries to communicate with the programmable logic. So a little example you can see here on the right, we can load our overlay or a bit stream through this overlay function. And this overlay class now can read whatever IP you have in your Avado design. And you can and Pink allows you to interface with this using Python libraries and make custom drivers and take it even further to integrate other libraries such as NumPy, SciPy, and even have like interactive plots with Plotly and maybe make some apps with IPy widgets. And this really helps with in terms of accelerating like results and making things look interesting, where we can quickly build apps and interactive plots. And this is all by default running with Jupyter notebooks, which is excellent for showcasing results. And if you push any of these Jupyter notebooks to GitHub via source control, you can see what you were running on the board directly in GitHub. So it makes it excellent for collaboration. So our Jupyter Lab perspective. So I've made an IPy widgets app here, which showcases one of the neural network instances that we've trained. So I think this one is the 16-bit weights and 16-bit activations. So let me go to the beginning. So on the left here, we have our different modulation schemes in the dropdown. And the play button just tells the cyclic buffer, send the data, and will constantly be receiving frames of data from the ADC. And then we can change the modulation schemes, we can change the SNRs, and we can, while it's running, sit and inspect the transmitted signals. And we can do this like without having to stop anything. So we saw earlier that the GFSK, so sorry, we started off with QPSK at 24 SNR, and we can see on the right here, we have the confusion matrix that tells us what our predicted label is and what our true label is, and what kind of confidence we had with that prediction. And we can see on low SNR, it's or a high SNR, it's pretty good. If we pick GFSK, lower the SNR a little bit, still does pretty well. But if we move to a different modulation scheme, such as QAM16, here, and we put that to maybe a terrible signal to noise ratio, we can see that the neural network's not really figuring it out that well, and it's kind of jumping around the place. If we increase it to 24 decibels, we see that it's still a little bit confused between QAM16 and QAM64, which I would expect, given that QAM16 and QAM64 are the most similar modulation schemes in this test. So how do we? There we go. Okay, so that was the interactive view. So here I've got a little bit more of a formalized set of plots here for the accuracies for each of the models that we're testing. So there's a lot of confusion matrices here, but if we start from the top left, we have an SNR of -20 decibels, and then it increments by 4 decibels going to the right all the way up to 24 decibels. So in terms of performance, we can see that at low SNRs, as we expect, it doesn't really know what's going on, doesn't know what modulation scheme is what, but we can slowly see that as the noise decreases, it starts to maybe figure out GFSK a little bit better. And once we get up to the maximum amount of signal to noise ratio, we get a better diagonal line, where we can still see here though that QAM16 and QAM64 is getting a little bit confused still, but overall we're getting okay performance. So if we compare this to our 8-bit weights, we can see a similar set of results. Actually, they're quite too similar, I guess. But yeah, it shows that 8-bit weights doesn't really drop in performance at all here. And then if we look at the 4-bit weights, we can see that there's a significant change here. So for 4-bit weights, it maybe improves from -20 decibels up to maybe 8, and then after 8, it doesn't seem to do any better. So I think we've hit a wall there. So we can kind of collate all this information and take the average accuracies for all modulation schemes for each of the models, and we can plot them on an SNR curve like this. So between 16 bits and 8-bit weights, we see an almost identical or equal performance for this. So that's an interesting output. But for the 4-bit weights, we see that we're limited at 40% SNR. So sorry, 40% accuracy. So maybe 4-bit weights is too little. But I think if we were to increase the size of the network, we could maybe make up for this loss in weight precision for the 4-bit weights. If we had a much larger model, we could make up for the fact that we don't have as many bits via adding more neurons in our network. And another thing that could maybe make the accuracy better is maybe train it in scenarios with fewer impurities. So maybe we don't include such a multipath channel. Maybe we include a simpler channel, and maybe it'll perform better. So in terms of resource utilization, so we saw that 8-bit weights and 16-bit weights are pretty similar. In terms of resource utilization, we see that the 16-bit weight model it uses the most resources out of all three. And so here, in terms of slices, they're pretty similar. Registers are pretty similar. DSPs are exactly the same. But in terms of the storage of the weights on chip, we see that the block RAMs reduces by maybe 6% from 16-bit weights to 8-bit weights. And between the 8-bit weights and the 4-bit weights, we see that there isn't a drop. So that must be some optimization that Vivado isn't doing. But I think it's safe to say that maybe the 8-bit weight model would be probably the best choice here. So we have the fewer resources and the same performance as 16-bit weights. So in terms of conclusions, presented the motivation for deploying deep learning for physical layer wireless comms, as in we want to swap out maybe some functionality that already exists in a radio receiver pipeline. We've introduced the challenge of modulation recognition and what the RFSoC is. The reasoning and the motivation for generating a custom data set where we want to maybe take into account what the RFSoC might be doing to the signal as part of the channel. But also we want to be able to snapshot a continuous signal that's coming into the model. Introduce the custom architecture that I built, which utilizes like a streaming-based convolutional neural network. And it uses a data flow-like structure, which can be seamlessly integrated into a wireless comms pipeline where samples are streaming in and samples are streaming out. And the data flow architecture, allows you to process every sample that you receive with no pauses, which is important, and makes it ideal for maybe some time or data sensitive physical layer applications. So in this example, we trained 3 networks at different weight quantizations and watch what kind of accuracy we had and what resource utilization they used. We saw that the 16-bit and 8-bit weight networks perform similarly, but the 8-bit weights use as many resources as the 4-bit weights. So it looks like that would be a good choice to make. But good resource usage overall, despite the fact that we're storing the weights on chip. In terms of future work, I think there is an angle that can be taken to explore training with lower quantization levels, even lower than 4. But as we can see here, maybe we want to increase the network sizes to make up for the fact that we're losing that dynamic range. And maybe we'd like to try an application where, like a regression application, where we're maybe decoding the signal or using it to channel estimate rather than a classification case, just to see how it holds up in that kind of scenario. So yeah, thanks for listening. I said earlier that our group provides examples on how to use the RFSoC through our GitHub page. That's here on the left, github.com/strathdr. We also released an RFSoC book last winter. Maybe it was earlier this year, but yeah, we finalized it last winter, and that combines maybe some communication theory with how to use the RFSoC. And alongside this book, we have got GitHub repositories to help you get started with the RFSoC. So yeah, thank you very much.